In this video, we're going to explore one of my favorite topics, which is the geometric interpretations of systems of equations. Now, in the case of just x and y, just two-dimensional case, this is rather easy. You know what 2x minus y equals 5 represents. Hopefully, it's just a straight line, and x plus 4y equals 7 is another straight line. So the geometric interpretation of those is just two lines intersecting at a point, and that point, x equals 3, y equals 1, that's the solution to the simultaneous equation. Hopefully that's something that you'd thought through before. A lot of people always sort of treat simultaneous equations as totally separate from equations of straight lines, but of course they're the same in two-dimensional geometry. What about the three-dimensional case? Well, we solved this one in the last video. Now, what are these? Well, they're not lines, and three-dimensional lines don't always intersect anyway. So let's jump over to GeoGebra and let's see what these are. Well, let's clear away this background plane, and let's take our first one, x plus y plus z equals 2. I think I'm just not looking at it from the right angle. There we go. So that is a plane. So that first equation there was a plane. Now we can put in the other one, which was 2x minus y plus z equals 7. And that was another plane, which GeoGebra has helpfully given the same color, but let's just change the color of that. And if we put in our last plane, we end up with 3 planes. And of course, 3 planes can intersect at a single point. Now, what is that point down here? Well, it's the point 1, minus 2, 3. It's the point that we found by solving the simultaneous equations in the last video. So the geometric interpretation of 3 planes is going to be, or rather of a system of simultaneous equations with 3 dimensions, is 3 planes. But they're not always going to intersect at one point. Now go back to the two-dimensional case and consider the fact that 2 lines don't always intersect at a point, because you might have 2 lines that are parallel, in which case you'll have no solutions. Or maybe you have 2 lines which are actually the same line twice, just right on top of each other, in which case you'll have infinitely many solutions. Now in 3 dimensions it's different to that, but nevertheless there are different sorts of setups for 3 planes, and maybe you want to think through what they are. Of course, one setup is just 3 planes all intersecting at one point. Let's think through what all the different permutations are for how 3 planes could interact with each other. Now, what might 2 parallel lines look like in their equations? Well, it would basically be something like 2x plus 3y equals 5, say, and 2x plus 3y equals something else, like 7. These are 2 lines with exactly the same gradient, but they're not on top of each other. Now, if we converted this into matrix form, we end up with 2, 3, 2, 3, xy equals 5, 7. Now, why can't we use our matrix inverse method to solve this? Well, because if you try to do xy equals the inverse of 2, 3, 2, 3 times 5, 7, you run into a problem because the matrix 2, 3, 2, 3 has no inverse. It's a singular matrix. Look, its determinant, 2 times 3 minus 3 times 2, is 0. So that's good, right? Because that confirms that there is no solution to 2 parallel lines crossing. But in 2 dimensions, it's not always either 2 lines intersecting or 2 lines parallel. You might have 2 identical lines that are on top of each other. If I gave you the rather bizarre simultaneous equation of x plus y equals 5 and x plus y equals 5, well, it's not that there are no solutions to that, it's that there are infinite solutions to that, right? X could be 1 and y could be 4. X could be 2 and y could be 3. X could be 100 and y could be minus 95, and so on. But look, the matrix corresponding to that is 1, 1, 1, 1. And that also has no inverse. So a matrix with no inverse indicates that it isn't just a simple case of things intersecting at a unique point, but it could either be no solutions or infinitely many solutions. Now let's jump over to the 3 by 3 case. So with this example, there was a unique solution and we found it. And lo and behold, if you were to work out the determinant of this matrix here, you'd find out that its determinant was not 0, i.e. it has an inverse. And since it has an inverse, there was a solution to this matrix equation. And we basically did that last time using our Gaussian elimination method. But what happens if the determinant is 0? Well, it's different to the straight line cases, but what is it? Maybe you could think through, what are all the different ways that 3 planes could be related to each other? Well, let's explore what that is now. So to start with, we've got our non-singular case, consistent case, which is 3 planes meeting at a point. It's non-singular because the matrix associated with the equations does not have a 0 determinant. So that's easy. If the matrix associated with the equations isn't 0, then there is just a single solution. It's the 3 planes intersecting at one point. But we could also have singular consistent. Now, what would that look like? That's going to look like 3 planes intersecting all on a straight line. That's called a sheaf. Now, in this case, there are infinitely many solutions. It's everywhere along that line. So we need a way to figure out when it's that, and we'll come to that in a moment. What else could it be? Well, we could also have singular inconsistence. That's where the matrix does have 0 determinant, so no inverse, so no unique solution, but it's something else. And one version of that is that it's a prism. So that is where we have 3 planes that have a prism running down the middle. And you can see there's no point where all 3 planes intersect, which means there's no solution. So that's what we'd call a singular inconsistent solution, and that's a prism. Now, of course, there are a few other arrangements. For instance, 2 or maybe even more of the planes might be parallel to each other. Now, if any 2 planes are parallel, then of course there'll be no solution, and that will always be inconsistent. So it could even be all 3 planes are parallel to each other. Now, we do have these funny situations where you've got all 3 planes on top of each other or something like that, and that would be like the equivalent of the 2 repeated lines. That's why we've got infinitely many solutions. And there's also the case where we have 2 of the planes are on top of each other and the other one isn't, and that's going to form a sheaf as well. Now, all of these cases down here that have parallel planes, they're pretty easy to spot because a parallel plane will be something like x plus 2y minus 3z or whatever equals 10, and then the same thing again, but equals something else, like 8. Or maybe it's in disguise, maybe it's minus 2x minus 4y plus 6z equals 3. This is parallel because this is just a multiple of that. So this would be an example of 3 planes that are parallel. So this is an example of this one. So these ones with parallel planes, they're rather easy to spot, and also generally not assessed that often because they're quite easy to spot. Really, our challenge most often, once we've established that none of the planes are parallel, is to figure out if there isn't a single consistent solution, whether it's the consistent sheaf or the inconsistent prism. So these are the different situations we can have, and in the next video I'm going to show you how to determine which of these setups it actually is. So see you there.